We're continuing on in chapter 10 with our second part of the lecture, which is going to be about displaying data. We want students to be able to understand and explain categorical and numerical data, basic plots and graphs, stem and leaf plots, histograms, and bar graphs, as well as circle graphs. Data analysis is going to refer to an informal approach in statistics. We are talking about young elementary school kids here. We're not asking them to find the variance or some complicated calculation. We're asking them to kind of do this in an informal way so that we can build upon it later. And the term data analysis is somewhat new. That's kind of come about with how we're scientifically dealing with things in society. So statistics once referred to numerical information about states, political territories, money, and it comes from the Latin word statisticus, meaning of the state. So a lot of things in statistics were originally related to political or state level information. Graphs, however, are what we use to tell a story. So statistics can be numbers, but we want to take those numbers and we want to tell a story about those numbers. So if I have this image here and I'm looking at that profit graph, I can look at that story and say, holy cow, something really bad happened. But if I was just looking at a list of numbers, that dip isn't going to be as obvious as I immediately see it here. Now, data, when we start teaching students to use the word data, they're observations. They could be a measurement, it could be a gender, it could be a survey response that's been collected. It doesn't have to be a number. Statisticians often collect data from a smaller portion of a larger group. That's our sample, in order to get information about the group at large. This information we then use to make hypotheses about the entire group. So let's say your school has 3 first grade classes. I could pick one of the 3 classes, get their responses, and then I could say, well, this one third grade class really represents all third graders in our school, so you can make a hypothesis about everybody from that smaller data set. Data can fall into many different categories to describe it. Categorical data is going to be categories. So it's when you fall into categories. So male or female, inside, outside, left, right, hair color, eye color. Numerical data is going to be number based. So your grade, your average, your GPA, a measurement of some sort. Those are going to be numerical data points. Now, numerical data points are great, but if we show anyone a list of numbers, it's not going to tell them a story. So a pictograph is one way to represent a tally of categories. It's not really used with numerical data, but say if I just listed out a bunch of eye colors, when you're looking at that list, your head's gonna swim a little bit and you're not gonna know what to think. But if I start using tally marks and I tell you, well, there's 10 tally marks for brown, 10 tally marks for blue, 5 tally marks for green, that's going to give you a really full picture a lot better than listing it out. We can also use symbols. So I could use a symbol to represent a quantity of items. So here, each little newspaper bundle represents 10 kilograms. So when I'm building this, I know that in July, I have 40 kilograms. And I've used the symbol, which is nice because if I was doing 40 tally marks, that would be a whole lot of counting for students. So sometimes you can use a symbol in that pictograph. The one thing we really want to stress when you're teaching graphs to your students is they all need a title. And if needed, they should also have a legend. If I don't have a title, I don't know what I'm looking at and there's no context. So here, if I'm looking at the number of students in each 5th grade class, I've titled it. I've got Hillview 5th grade student distribution, and then I have a legend for the symbols. That is incredibly important in your classroom that you're making sure to give that distinction. A dot plot is another visual method we can use to show data. In a dot plot, it gives a quick and a simple way of organizing numerical data, and they're typically used when there is only one group of data with fewer than 50 values, because beyond 50 dots, it gets really hard to look at. So let's suppose the 30 students in this class receive these test scores. I'm going to put a dot on the plot for each test score. If I have multiple test scores in one category, I'm going to stack the dots on top of each other. And this tells us a really complete story. I can see the most repeated score is an 82. I can see, wow, only one student got a 52, and then there's a huge gap. So most students kind of cluster together around 70 to 87. And here's some other things we can work on looking at from that. We can see outliers, we can see clusters, we can see a gap. So there's a lot of different ways to describe a dot plot. Here are some definitions to help you as you describe your dot plot. We use outliers, clusters, gap, and then a mode is going to be the data value that occurs the most often. So here we said 4 students score an 82. That's the most frequently scored value. So 82 is the mode. If a dot plot is constructed on grid paper, then we can shade the squares, or we can really shade those X's, and we can add a vertical axis that gives us an idea of those values. You see the 1, 2, 3, 4, that just makes it a little bit easier to look at, but not every classroom is going to have access to that graph paper. Stem and leaf plots are similar to a dot plot, except for we separate the numbers. So 52 has a stem of 5 and a leaf of 2. So see that 5 bar 2. Here we have 70, 72, 72, 73. So the nice thing is you can see those repetitive values here in the stem and leaf plot as well as in the dot plot. If it's an ordered stem and leaf plot, the data goes from an order from least to greatest. Here are the advantages of a stem and leaf plot. They're easy to create by hand. You don't have to have students that are fantastic at the letter X. They do not become unmanageable when there's a lot of data. So unlike the dot plot, which can get really difficult to read, these are slightly less difficult. No data values are lost. But a disadvantage is we may know that a data value exists as far as like the mode, but it's not easy to tell which one would be the mode. It's hard to track how many times data values are presented in reference to another, because I might see a 2 4 times, but maybe there's a 5 4 times or a 4 4 times or things like that. How to construct it, we're going to follow some steps. Find the high and low values, decide on the stems, then list the stems in a column from least to greatest, and use each piece of the data to form the leaf on the other side. If the plot has to be ordered, list the leaves in order from least to greatest. Then add a legend so that you can easily identify things. Add a title explaining what the graph is about. As always, a title is so necessary. We can also do back-to-back stem and leaf plots. This is not something for your lower grades. This is something for your higher grades as we really start exploring stem and leaf plots. When we do a back-to-back plot, we're using that to compare two sets of related data. In this plot, there's one stem and there's two sets of leaves, one to the left and one to the right. Here's an example as well. We also have presidents that are grouped into two groups. We've got George Washington to Rutherford B. Hayes and James Garfield to Ronald Reagan. Then we're putting their information for their age at death. We separated them into these nice columns to help us sort the data appropriately. We can take this information and create a back-to-back stem and leaf plot of the two groups to see if there appears to be a difference in ages between the death and the two groups. And we can also use that to see which group of presidents seems to have lived longer. So when I create the back-to-back stem plot, this is what I see. I see the first 19 presidents are on the left, and the remaining 19 presidents are on the right. 38 with the 3 and the 8 represents 83 years old. This is why I said we don't want to use this with younger students, because they're going to say the 3 and the 8, they're going to say, oh, 38. It's really 83 because it's the left-hand side of the stem and leaf plot. Whereas on the other side, 6 and 7 does represent 67. The early presidents seem on average to have lived longer, and then we can possibly add a little bit of interpretation to that for why, but we really want to just focus on what do the numbers show us. So when I'm just looking at those numbers, the ages at the high end, really especially through the 70s and the 90s, come more often than from the early presidents. The ages at the lower end come more often from the later presidents. So, for the stems in the 50s and 60s, the numbers in the leaves are about equal. A stem in a leaf plot shows how wide of a range of values the data covers, where the values are concentrated, and whether the data have any symmetry, where gaps in data might be, and whether any data points are decidedly different from other data values. Moving on from stem and leaf plots, we have what we call a grouped frequency table, which is a similar concept, but not exactly the same. This shows how many times data occurs in a range of values. The data for the ages of the presidents at death is summarized in this table slightly differently. You'll notice a grouped frequency table uses the tally marks that we just saw in the previous thing. Characteristics of frequency tables include each class would have some sort of interval that's going to have the same size. So we're grouping clusters of values there by the same size. The size of each interval can be computed from subtracting the lower value and the higher value and adding 1 to it. We know how many data values occur within a particular interval, but we may not know the actual values themselves because we're just seeing the tally marks for how many numbers fell in that interval. As the interval gets really big, though, this is where we see issues because it's not clear what the actual values are. Classes should not overlap. So when we're looking at intervals, there should be no overlap between those intervals. And in a histogram, we're going to see why that is in just a minute. In the frequency table, we don't have any overlap. The same is true of a dot plot, the same is true of a stem and leaf plot. But once I had a histogram, those are made up of adjoining rectangles that touch, or bars. The bars are the same width, and the scale on the vertical axis must be uniform, but notice how they touch. So there's not really an overlap that occurs here, but look right here, like at 50. 50 is the end of one bar and the start of the next. So technically, that could potentially be seen as a slight overlap. A bar graph, on the other hand, does not touch. So the bar graph of the bars are going to be separate, and a lot of times a bar graph is going to be used with categorical data. So I'm going to use that a lot with categories and not as much with actual numeric data. A distinguishing feature between the two is that there's no ordering that has to be done with the bars in a bar graph, whereas a histogram is used with numbers and clearly has an order. A double bar graph can be used to make comparisons in data. So maybe, and this is not the best example, but maybe I want to know about girls versus boys. So I could use a pink bar for girls, a blue bar for boys. Or maybe I want to know about blondes versus brunettes. So you can show two bars at one time. They're going to be a little bit skinnier, but they're going to follow that same frequency value. Now, a table for other bar graphs, the table can be used to give categorical data with a frequency. The figure here depicts a percentage bar graph with the exact same data. So see how the percentage is given here in the data. I have the frequency, and when I'm doing that, it's going to go from kind of 0 to 100%, or 0 to whatever percent you have there, and you're just going to show. So 4% should be less than 14%. Is it an exact measurement? No, it's not exact. This is a sketch, it's an estimate. So you're teaching your students to estimate how big one percentage is in reference to another one, which really teaches them some really great skills. This table shows the information about expenditures of a business over some length of time. They can then take a stacked bar graph with that same data. So instead of having two bars next to each other, now I'm combining them into one category from 1970 to 1979, and I'm showing the percentage that was material versus the percentage that was labeled, and together I can see from the chart they add to be 100%. A circle graph or a pie chart is going to be kind of in a whole league of its own. It's used to represent categorical data. It does not represent numbers. It is consistent because it's a circular region where each section is going to represent some part or percentage of the whole. It shows how the parts are related to the whole. So if I want to construct a circle graph for this information here, I first have to figure out, well, how many total do I have? Well, I add up all of them together. I have 710 people. The measure of the section of the pie graph is found by finding the fraction or percentage that the section represents. So if I want to look at first class passengers, there were 202 first class passengers out of the 710. So I'm going to do 202 divided by 710, which is 28 and a half. I'm going to follow that same theory for the other classes until I have a list of percentages that should add up to be 100%. Then I'm going to sketch it, and my section should be approximately proportional in reference to one another, meaning that 29.9% is bigger than 28.5. Are we asking students to measure this with a protractor? No. This is an estimation once again. We just want them to estimate this. So we're not trying to be super exact when we're teaching this. We're looking for an estimate. Here's another example of another pie chart. Here, look at this again. My percentages look accurate when I reference them all together.